What we're going to do today is, whatever time we have, basically two examples that are related with population dynamics. And you may say, but I'm not in biology, why should I care? Because actually the same model, the same sort of models can be applied between competing mechanisms in any problem. I mean, in mechanics, in materials, in fluids, in electrodynamics, anywhere where you have two competing mechanisms, you can use the same ideas, but obviously these are very easy to discuss about in the context of population dynamics. So what the idea here is we have two different populations of two different species that compete with each other for food, basically, and we want to know if there is any steady state where maybe both species survive or maybe only one survives, okay? And the models we're going to cover will be very elementary, and the only purpose is to demonstrate the ideas of stability of nonlinear systems. All right, so actually, let me go directly to the equations that you see on the bottom. So if I assume that I have, so X is the population of one species and Y is the population of another species, the two equations that you see for the growth of the population X and Y, here is when there is no competition between X and Y. So the two species live on their own, don't bother each other. So epsilon 1 here, for example, is the growth rate of X, right? You can see dx over dt equal X times epsilon 1. And then by having this term minus sigma 1 X, effectively we're saying that there is a saturation point in the population. They are not going to keep growing to infinity, and the saturation rate, you can see it is epsilon 1 over sigma 1. Okay? So again, epsilon 1 is the growth, and epsilon 1 over sigma 1 is the saturation rate. So the same thing for Y. Again, in these two equations, there is no competition between the two species. So now what we're going to do is we're going to introduce some competition, and the competition is going to come like that. Obviously, if there is Y that is eating the food of X, the growth of X is going to be reduced, and also the saturation rate of X is going to be reduced, right? Common sense. Now, and similarly, if there is X, the growth rate of Y is going to be reduced by this factor, and also the saturation rate for Y is going to be reduced accordingly. Now, let me just say that these models will be very easy to analyze and discuss stability, but you will see, you already have read the slides, I'm trusting, that the answers depend to a significant extent on the values you give to these parameters. And that's not an obvious task, because if, for example, you do a very small mistake or somehow you try to compute the sensitivity with respect to these parameters, you will see the results change drastically when these parameters change. And that's a very difficult problem. Welcome, guys. How was the fluids? Excellent? All right, I hope to hear that for the math exam as well, after 3 hours. All right, so again, something that I need to make it clear is that the values of these parameters affect things drastically, and there's no easy way to figure out what those parameters are, all right? So right now, we're assuming we know these parameters. Okay, so what I'm going to do is I'm going to take a very specific problem with the epsilon and sigma parameters that you see here. So this is dx over dt. It's almost linear, all right? So there is some bilinear terms, xy and xy, but nothing major, no significant nonlinearities. And immediately you can see the critical points are the solutions of this equal to 0 and this is equal to 0. So if you take all possible combinations, there are 4 critical points. You're going to have to do this on the exam today as well, right? So there are 4 critical points here, and those are 0, 0, 0.75, 1, 0, 0.5, 0.5. And you can appreciate here, when you have 0, 0 means no species survive. That's really bad, isn't it? I tried to wait. I did my best. That's okay. You had to take a break too, right, after the exam. All right. So 0, 0 means that no species survive. 0, 0, 75 means species X dies. This is species Y dies. And 0.5, 0.5 means they're both happily in equilibrium together, right? So we would like to know, well, I mean, when I say they're happily in equilibrium together, assuming that this is a stable point, we don't really know that, okay? But these are the critical points. So if these 3 points, for example, are stable points, or any of them stable, means only one species is going to survive. All right, so I'm going to take you very fast through the results because they are sort of trivial. This is the phase space and how the derivatives, the relation of y and x looks like. So there are 4 critical points. Again, I mark them with these dots there, all right? And you can actually, from looking at the arrows here, you can immediately see you know, which points are stable and which are not. But I want to do the formal analysis for a second, all right? So what I'm going to do is I'm going to take, let me see, I'm going to take 1 point at a time. To do that, we have to, I remind you, when the critical point is not a 0, 0 point, you have to use new variables that are x minus x0 and y minus y0. So you basically have to move the critical point always to 0, 0. And that's why you see now from the variables x and y, I have moved to the variables u and v that are x minus x0 and y minus y0. So for example, for the 0, 5, 0, 5 critical point, your variables will be x minus 0.5 and y minus 0.5. And this is the Jacobian matrix as we discussed. You know, after you do linearization, there is no constant term. You drop all the higher order terms, and this is what you get. All right, so the Jacobian, if you calculate derivatives with respect to x, right, you have x minus x squared minus xy. You get this term, minus 1 minus 2x minus y. If you take derivatives with respect to y, you get minus x. And the same thing for the term on the right-hand side of dy over dt. So that's the Jacobian matrix. So you go point by point. The point 0, 0, you plug in the Jacobian matrix 0, 0, you get 1, 0, 0, and 0.75. So the matrix looks like that. Now, in an exam, you're not going to have time to actually calculate the eigenvalues and eigenvectors. So what are you going to do? I don't really want you to calculate the eigenvalues and eigenvectors. You know what you will do? Here is what you're going to do. You're going to have this nice picture with you, in front of you, and say, what is this picture telling me? I need to compute P and Q. So what is P in this problem? What is P in this problem? Which is equal to, because we're not going to compute the eigenvalues, it's equal to 1.75. And what is Q? Q is the determinant. And how much is that? The determinant is 0.75, okay? It's 1 times 0.75. So P is equal to 175, and Q is 0.75. So P and Q are both positive. And now, if both are positive, obviously you need to decide. You remember, so you are on the, I'm looking on my nice plot. I am on the right upper hand side, okay? So you're going to have to decide if delta is positive or delta is negative also, because you get different type of critical points. And what is delta? It's P squared minus 4Q. So if you do all of these calculations without computing the eigenvalues and eigenvectors, you actually figure out that this is an unstable node, okay? In the context of the eigenvalues, you can see you get e to the t and e to the 0.75 t. So this thing takes you away from the critical point. So this is an unstable node. All right, so you do the same thing at the point 1, 0. And now you have to use new variables. So u is going to be x minus 1. V is going to be equal to y, basically. So you plug in the coordinates 1 and 0 in the Jacobian. This is what you get. You repeat the same calculations. And the solution looks like that. So I see one eigenvalue is negative, one is positive. So what type of point is this? It's a saddle point. And is it stable or unstable? Unstable, thank you. It's unstable. I mean, as soon as you see something, you know, here immediately to the something, right? But again, I don't want you to have to compute all of these things. You compute P and Q, and if you need, you compute delta also, which is P squared minus 4Q to make your conclusions. All right, and again, this is the critical point 1, 0, all right? And you can see, all right, in the horizontal axis, everything comes towards this point, but basically, in every other orientation, things are running away from that point. The point 0.075, you repeat the same calculations. And what type of a point is that? What point is it? Saddle point, and it's unstable, obviously. And so we go to the last point to see if there is anything that is going to come to be stable. So the point 0.5, that says basically that we have, if this turns out to be a stable point, so basically the populations balance each other, all right, and live in harmony. So if you actually calculate the eigenvalues and eigenvectors, it comes both eigenvalues to be negative. All right, so what type of a point is this? This is a node, but it's an asymptotically stable node because both eigenvalues are negative. All right, so that's nice. And if you try to actually plot some of the trajectories, you will see that a lot of these trajectories, all right, when you come, they approach basically the point 0.5, okay? You can see it, all the trajectories come this way. And actually, if you are coming from infinity, you can see that the growth rates are negative, right? If x and y are very big, 1 minus infinity, all right, is negative. And because the growth rate is negative, you can see the trajectories are coming inwards towards the 0.5 point, okay? Now, if you're going to have to plot something like that, and obviously you will have to plot something like that, I advise you use common sense and you plot it with common sense, unless you already have a program that can do this for you, all right? But you don't really need anything. But if you know what type of a point is, everything, right, you should be able to plot this nicely. Okay, now, if we change a little bit the coefficients, right? I mentioned before our fluids class came, I mentioned that the results can be day and night if the coefficient change even a little bit. So here what we have done is we have the same problem, but the coefficients are a little bit different. So let's repeat the calculations without doing the algebra. We get 4 critical points that you see here. So in 3 of those, one or both of the species die, and the other one, if it's a stable point, we have the species in equilibrium. So let's repeat the calculations. Okay, so you calculate the Jacobian. You go through 0, 0 point, and it comes immediately that the 0, 0 point, I can see both eigenvalues to be positive and real. So this is an unstable node, okay? And if you look at the point 1, 0, look what happens now. Suddenly 1, 0, I can see both eigenvalues being negative, right? So this is an asymptotically stable node, which means one of the species survives only, all right? So 1, 0 is asymptotically stable. And how about 0, 2? Asymptotically stable as well. So depending on the initial conditions, either one species will survive or another. And you may say, is it possible for both of them to survive? And if you take the 0.5, this was asymptotically stable before, But look what happens now. One of the eigenvalues comes to be positive, so the answer is no. This will be unstable. So again, a very small change in the coefficients changes the answers. That's not good news, right? Because how do you calibrate these coefficients? And that's another topic. It's a statistical topic. You have to collect data, and you have to do some inference. And that's another course that is not relevant to what we do right now. OK. Now, I want to plot what happens on the phase plane, because this is going to come also on the exam today. So you remember we have 4 critical points, right? So I see 1, I see the 0.5, 0.5, 1, 0, and 0, 2. And we said this is an asymptotically stable point. This is an asymptotically stable point. And you can actually see, like if I look at this point, every path that starts nearby, right, approaches this point 1, 0. Now, I want you to look at the trajectory that converges towards the 0.5, 0.5 node, all right? What can we, I mean, I call this the separatrix from separation, I suppose. So these trajectories that approach this unstable node, what do they do? Look on the top. So if you're coming from infinity, all the trajectories take you where? To this stable point. If you come from down there, all the trajectories are taking you to what point? The 1, 0. So these trajectories that are marked there as separatrix, effectively, they separate 2 different types of trajectories. One that converges towards this asymptotically stable point, and another one towards the point 1, 0. Now, you should be able, all right, you don't have to do any calculations, you should be able to identify in your problem if actually you do have a separation of the trajectories, and if you do, you should be able to identify nicely what this trajectory that does the separation is all about. Yeah, it is. So it is a trajectory that separates, you know, 2 different types of trajectories, basically. And you may actually have, in a more complicated problem, you may have multiple of those, right? I mean, you can imagine a very complicated scenario. You may have multiple of those, but for our problems, it looks as simple as that. And by the way, whatever I mentioned on coming from infinity, you can see if you come from minus infinity, these trajectories here, they also go to 0, 2, and the trajectories from below, they also go to 1, 0. So the separatrix here also includes the trajectory that you see. You can see it, right? There is another trajectory from 0, 0 to this unstable node as well there. As we have marked those with another color, but you know, they do the job. Okay. Now, you can generalize this thing, right, and do the analysis for, without putting any numbers. You can actually do the calculations with just symbols. And I am not going to repeat this since we don't have much time today. But let me just say the following, right? If somebody asks you, so these are the general growth equations of 2 species, okay? And somebody asks you, can you have the 2 species in coexistence? So if that's the equation, coexistence means you don't really want to have x equal to 0 or y equal to 0, all right? So coexistence means this thing inside the parenthesis has to be 0, and this other thing inside the parenthesis has to be equal to 0. So you're asking, can I actually find a critical point defined by this parenthesis 0 and this parenthesis 0 that's a asymptotically stable point, okay? So the first thing is, can I find an x and y that solves these 2 equations, okay? And actually, if you actually plot these equations for different values of the parameters, you have these 4 different situations that you see here. And obviously, on the first 2 cases, they don't intersect. So obviously, you cannot have coexistence in this case. Now, the other 2 cases, they intersect. So this is a possible coexistence. You don't really know if it is stable. This is also a possible coexistence. You don't really know if it is stable. So what you need to do is you need to take this situation and that, and now plug this inside your Jacobian, if you like, and look at the linearized equations and see if this point is stable and this point is stable. So I'm going to give you the answer because the algebra is basically identical to what we have done. The only point that's asymptotically stable, the only situation you can get this, is when the parameters epsilon and sigma for the two species are giving you a situation that looks like this situation here. So it comes that C is not an asymptotically stable node, okay? So it may be, but this is the only situation. And when exactly do I get this? Here is the answer, if I can find it somewhere. So when you do the linearization and nothing, exactly the same thing, but with no numbers. So I'm going to give you the answer. So the answer is if sigma 1, sigma 2 minus A1, A2 is negative, all right, the eigenvalues are real and of opposite sign. You can see if this is negative. So one of the eigenvalues is going to come to be positive, another one is going to be negative. So this is a stable saddle point. So the only way that you can get an asymptotically stable node for these general models is if this condition is satisfied. All right? Sigma 1 minus sigma 2 minus A1, A2 greater than 0. And I remind you that sigma is used to define sort of the saturation point of species X, if you like. All right? It's like basically how the species controls its own growth. And the coefficients A1 and A2 define in some ways how one species affects the growth of the other species. So if the effect of the species on each other is weak, all right, then this will be positive, all right, and in that case, they can coexist together. And again, the analysis comes simply by computing the eigenvalues and looking at this equation and say, if this is negative, I'm going to get two real eigenvalues, plus and minus, so this will not do it. And if this is positive, things look very good. And in the four situations that I showed you, if I can go back to this picture, this is the only situation that actually satisfies that condition. Okay? So you can look at the nodes, and that's the only situation. Okay. So let me do another case, another example. If I can find it. All right, so we're going to assume that we have two species. One species goes and eats, the grass in your yard, but the other species that we call the predator eats the prey. So one animal eats, its food is the other animal, all right? So effectively, the growth of the predator depends on how much prey you have, all right? And how much prey depends on how much predators you have. So the question is, can you have these two things in coexistence? Now, again, it may sound, why do I care about this dynamical system? Because it's a standard dynamical system in, if you take a course on dynamical systems, don't know there is one, all right? There should be 10. But if you look at books, this is basically chapter 2 in every book on dynamical systems. It's a very fundamental problem. And the only difference from before is you had the two species before competing for the same food. Here, the prey eats whatever likes to eat, but the predator eats the prey. Okay? So what's the model looks like? So let me just find where the equation is so we can finish this. So this is how the equation is, okay? So let's look at this equation. Let's say that, so X is the prey, okay? And let's say that there is no predator, so obviously A is the growth rate of X if it lives alone. Okay, that makes sense, right? In some sense, it will not be a realistic model because it tells you that X will keep growing exponentially So it doesn't have this steady state that we had before. But beyond that, A is the growth rate if X was alone. Now, if the predator is around, why do I remove minus something times xy? What is the idea here? Why do I have xy and not just y? Why do I say that the growth rate of the prey will be decreased by proportionally to x times y? How do you understand that? Why I don't say that it will be reduced proportionally to how many y's I have? I mean, so the two species have to interact, right? And the question is, how many interactions, how many times they get together, right? And that is proportional to the product x times y, okay? So, and obviously, in the prey case, the growth rate will be reduced by some proportion of xy. On the predator, on the other hand, will increase by something proportionally to xy, okay? So this is sort of a fantastic model, and again, is chapter 1 or chapter 2 on every book in dynamical systems, because it contains many of the essential things of very complex dynamical systems that we will not be able to cover in this class, okay? Now, do you have the machinery to actually analyze it? Yeah. I mean, this is almost, I only see some bilinear terms xy. It's not highly nonlinear. So you can actually compute the Jacobian. You can compute the critical points. You can see what is stable, what is not stable. So let's figure out. So the critical points, obviously, how do you compute? So I'm taking a specific example for demonstration. So the critical points, you will set this equal to 0. You will set this equal to 0. And the critical points come to be 0, 0, and 3, 2. Okay? And you can see these directions diagram in the phase plane here, all right? So this is the point 3, 2. And this is 0, 0. Actually, just looking at this picture, can you guess what is going on? Just look at the picture. So what do you think happens at what type of point is 0, 0, 3, 2? What type of a point is what do I have at 3, 2? How do we call that point? Say it again. Center, right? I have an oscillatory motion around that point. It's a center point. So it's a stable, but not asymptotically stable. Okay? We have to figure out, we don't know yet, but it is stable because if you are around this path, you will remain around this path, which, you know what it means? It means that the population of the prey and the predator, they oscillate. So one increases, the other reduces, but then they if the predator increases, it will reach a maximum, then it will start decreasing, and then the prey will start increasing. There will be some oscillatory variation in the population of X and Y. And of course, you can look at what is this point 0, 0 here. I mean, immediately I can see that there is a path directly that takes you away from the node 0, 0, right? So this is not a stable node. All right, so if you do the algebra, you calculate the Jacobian, take derivatives with respect to X and Y, you plug them in, and then you're ready to do your analysis. So you take the critical point 0, 0, you compute the eigenvalues, and you don't have to compute the eigenvalues. You compute P and Q and delta if you need. And in this case, you can see that one of the eigenvalues is positive, all right? So this is an unstable node, okay? And how about the other point? If you take the point 3, 2, remind you have to define new variables, x minus 3 and y minus 2. So you make this to look like the point 0, 0. If you repeat the calculations, not surprised, all right? The eigenvalues come to be pure imaginary numbers, right? Conjugate, okay? That's why you get a center. And so this is a stable center node, okay? We have seen this before. And somebody may ask you, we haven't actually explicitly done this. I kept saying in the lectures, you get these circles. Really, they're not circles. They may be ellipses, or they may be sort of elongated ellipses, okay? So if somebody tells you, okay, you have these nice closed paths for the linearized system, but are they circles? Are they ellipses? What are they? And you can actually compute them directly from this linearized system of equations very easily, because if I compute the ratio of dv over du, all right, and dv over du, I can write it like that. So dv over dt is, this is 0.5 u divided by minus 1.5 v. You notice here that I get a separable equation for u and v. So actually I can integrate, and when you integrate, this equation looks like that, where k is a constant. What type of equation is that? That's an equation of what shape? It's an ellipse, all right? So, but remember, this is an ellipse for what problem? For the linearized problem. All right, it's very important, because somebody asked me the other day, do you actually get the right solutions of the nonlinear system doing the linearization? The answer is no. This is sort of only qualitative information, right? So for the linearized problem, so it looks that around the 0.32, the particles, the population follows these ellipses, but the actual system, we don't really, we hope that it follows at least some closed path, but certainly there's no guarantee that those closed paths will be ellipses. So can you actually compute for this problem what the paths of the nonlinear system would be? The answer is yes, because also you can get a separable system of equations for y and x. You can actually solve this and compute this path. So this is my original system, all right? And if I write this as, if I divide them and I write dy over dx equal to that, you can bring the y's on one side, the x on the other side. And without any effort, you can actually compute that the trajectories you get are equal to that. Now you are going to have to plot it numerically, right, to convince yourselves that these trajectories are actually closed trajectories. So they are actually not ellipses. They look much more complicated, but they're closed trajectories. So the ellipse was not a bad approximation, okay? And if I plot them, this is how the exact trajectories will look like. And you notice some of these trajectories are very elongated, all right? So obviously they, the only thing you can say is you have closed trajectories. So there is some sort of oscillation, but obviously it's an oscillation of a nonlinear system, right? And you can see this is the answer from the exact nonlinear problem. So let me see if I can actually plot. So what I'm going to do is I'm going to plot the population x and y as a function of time. And you can, with some initial conditions, and you can see here the variation of the prey on the top. The predator is on the bottom. And immediately you can actually see that the oscillation is sinusoidal-like, all right? You can actually see that the predator is out of phase from the prey by some distance. That actually comes to be a quarter of the period of oscillation that you have here. And also you can actually, when you look at this plot, can you actually understand why it looks like this? So you start at, let's say, at time 0, when both populations are very small. So you notice the prey keeps increasing. Why is it increasing? Because there is not too many predators around. All right? So now, as the prey increases, there's more food for the predator. So the predator starts increasing as well. But the more the predator increases, the more it will eat of the prey. So the prey population will have to go down. And then you are coming back to the same oscillation. So the two species are happy together. They eat each other. And, and the cycle of life is continuing. So actually, you can, for the linearized problem, you can, for the general case, right, with any coefficients that you see up there, you can compute everything analytically if you like, okay? So I'm just going to give you the answers only for the oscillation. These are the ellipses that I mentioned, so there's nothing new. And you can find actually the nonlinear trajectories as well analytically. Okay, the similar equation with what we had before. And I only want, there is a formula with the sines and cosines. Come on, where are you? So here is the answer. So if you take that critical point and you try to compute for the linearized system this oscillation of u's and v's, this is what you get, all right? You get everything in a very nice closed form, and you can appreciate first why they are out of phase. This is a cosine, this is a sine. So you have pi over 2 on a period of 2 pi. So there is a quarter period lag. You can see the amplitudes and how they vary. And also you can compute the frequency of oscillation and anything else you want to. Okay? Now, certainly this is not a very realistic example, right? You only have 2 species. I already mentioned one deficiency when you look at the growth of one species without the other on it. There is no saturation rate, so that by itself is not quite right. So you may want to change that and introduce a saturation rate the same way we did on the first example. But more or less, this example and the previous one on 2 populations eating the same sort of food are, if you generalize them, you can get very good models for competing mechanisms in many scientific and engineering applications, not just in population dynamics.